For 70 years, the dogfight was a primal dance. One pilot, one jet, a visceral struggle for dominance culminating in that glorious, singular victory roll. It was a contest of skill, courage, and G-force endurance. But let's be brutally honest, that sky you think you know, it's already obsolete. The very notion of aerial combat, as we've understood it for generations, is being rewritten at speeds that would make your head spin. Imagine this. Tomorrow's first shot won't be fired by a human hand, nor will it be aimed by a human eye. Nope. It will be launched by a cold, calculating algorithm, guided by a self-organizing swarm of machines, and delivered at a mind-boggling Mach 7 before the enemy radar even finishes its first sweep. We're talking about a future that isn't just around the corner. It's already here, taking off from runways today. This isn't science fiction anymore. It's the new reality of military aviation, and it's going to fundamentally change everything we thought we knew about air power. Get ready because the skies are about to get a serious upgrade, and the rules of engagement are being rewritten in real time. Section 1. The problem no one is talking about right now. The best fighters on the planet, the F-35, Russia's Su-57, China's J-20 are already struggling against a new set of game rules. It's like bringing a finely tuned, championship-winning race car to a whole new sport. The advanced stealth shaping that took decades and billions to perfect, turns out it can be peeled apart by low-frequency AESA radars which, while not offering weapons-grade targeting, are more than capable of telling you something big and expensive is out there. Suddenly that invisibility cloak isn't quite as impenetrable as we hoped, forcing these cutting-edge platforms to operate with a new layer of vulnerability. Then there are the surface-to-air missiles. We're not talking about the old stuff. Modern SAM systems have pushed their engagement ranges past an astonishing 400 kilometers. Think about that for a second. An F-35 designed to operate in contested airspace now needs to worry about threats from distances that once seemed unimaginable. This effectively means that an entire squadron can be held at arm's length or worse, put in extreme peril, long before they can even get within their own weapon engagement zones. This dramatically shrinks the operational envelope for manned aircraft, forcing them to fly longer, riskier routes, or face devastating consequences. And let's talk about cost. A single Patriot battery, for example, costs less than 1/5 of an F-35, yet it possesses the capability to deny airspace to multiple F-35s. The economic asymmetry is staggering. You can buy a lot of Patriots for the price of a single stealth fighter. This isn't just a budget issue. It's a strategic one. Adversaries can deploy layered air defenses at a fraction of the cost of the aircraft designed to penetrate them, creating a truly unfavorable cost-exchange ratio. This means we're spending fortunes on platforms that are increasingly expensive to operate and deploy against threats that are comparatively cheap to field. Meanwhile, our pilots, incredible athletes and minds that they are, still max out at 9 Gs. They fatigue after 8-hour missions, their bodies and minds pushed to the absolute limit. And let's not forget the logistical tail. These high-performance jets need massive, glowing-on infrared tankers to extend their range, turning what should be a stealthy operation into a beacon for enemy sensors. The physical and cognitive limitations of human pilots, combined with the sheer economic and logistical burden of traditional manned air power, are creating a brutal math problem. It's a stark reality. Traditional manned air power is, quite frankly, pricing itself out of relevance, becoming too expensive, too vulnerable, and too limited by human biology to dominate the future battle space alone. The current paradigm is unsustainable, and everyone in the know understands that a radical shift is not just desirable, but absolutely essential for maintaining air superiority. Section 2. The family of systems. So, if another fighter isn't the answer, what is? The solution isn't a single shiny new aircraft. It's a collaborative, interconnected family of systems, a sophisticated ecosystem designed to operate as one. The Air Force calls it NGAD, for Next Generation Air Dominance. The Navy, not to be outdone, has its own version, the FAXX. But despite the different acronyms, both share a remarkably similar blueprint, a vision for air power that's nothing short of revolutionary. At the heart of this family is a manned flagship. Think of it as the quarterback, the mission commander, the strategic brain in the sky. But this quarterback isn't alone. It's surrounded by a cloud of cheaper, unmanned, loyal wingmen, These aren't just drones. They're intelligent, semi-autonomous or even fully autonomous platforms designed to extend the flagship's reach, sensing capabilities, and lethality. They can perform tasks too dangerous, too dull, or too distant for a human pilot. We're talking about a distributed force multiplier, where each element contributes to a greater whole. This family also includes hypersonic standoff weapons, capable of striking targets at speeds and ranges that render current defenses almost useless. These weapons aren't just fast, they're maneuverable, making them incredibly difficult to track and intercept. And what stitches every single sensor, every single shooter, every loyal wingman, and the manned flagship into one cohesive living organism? An advanced artificial intelligence backbone. This AI isn't just crunching numbers, it's dynamically managing the entire battle space, processing vast amounts of data in milliseconds, identifying threats, allocating resources, and optimizing mission parameters across the entire formation. It's truly a quantum leap in warfare. Imagine that quarterback plus a whole team of wide receivers, running backs, and defensive linemen. Except these receivers are drones that can ram the enemy if the playbook says so. A truly radical concept of sacrificial autonomy in service of the larger mission. This shift recognizes that the complexity and lethality of modern air combat demand a networked, resilient, and adaptable system, one where the strengths of human decision-making are augmented by the speed and endurance of AI-driven machines. It's about creating a synergistic force that is far greater than the sum of its individual parts, ushering in an era of true multi-domain, network-centric warfare. This isn't just an upgrade. It's a complete reimagining of what air superiority looks like. Section 3. Collaborative Combat Aircraft. If you want to see this future in action, the Collaborative Combat Aircraft, or CCA, is absolutely the poster child for this seismic shift in military aviation. These aren't just concepts on a whiteboard. They're real flying machines that are already redefining what's possible. In fact, 2 versions are already in the air, pushing the boundaries of autonomous flight: General Atomics Gambler and Anduril's Fury. These aren't scaled-down toys. They're serious pieces of hardware, each about 25 feet long, roughly the size of a light business jet. And here's where it gets truly interesting: the cost. Each CCA is projected to cost about $15 million. To put that in perspective, that's less than the cost of a single advanced air-to-air missile for some legacy platforms, and significantly less than the price tag of a modern manned fighter. Despite their relatively low cost, these CCAs are far from defenseless. They're designed to carry a potent punch, with internal bays capable of housing 2 AIM-120 missiles, giving them genuine air-to-air combat capability. They can also be configured for other roles, like electronic warfare or intelligence gathering, making them incredibly versatile. The beauty of the CCA concept lies in its collaborative nature. A single F-35, for instance, won't be flying alone. It can effectively boss or control up to 4 CCAs simultaneously. Think of the pilot in the F-35 as a mission manager, a conductor orchestrating a symphony of unmanned assets. The AI on board the CCAs and integrated into the manned platform reasons in milliseconds, making instantaneous, complex decisions that would overwhelm a human pilot. It can allocate targets across the formation, jam enemy radars to protect the manned asset, bait incoming missiles by presenting itself as a more attractive target, and even if the playbook dictates, sacrifice itself to save the more valuable mothership or achieve a critical mission objective. This kind of distributed decision-making and tactical flexibility is unprecedented. The sheer confidence in this technology is evident in recent budgetary decisions. Congress just doubled the FY25 buy of CCAs to a staggering 1,000 airframes. Let that sink in for a moment. That is more unmanned fighters than France has Rafales, one of Europe's most advanced manned fighter fleets. This isn't just an incremental increase. It's a clear signal that the Pentagon is fully committing to this new paradigm of air power. This massive investment underscores the strategic imperative to field affordable, mass-producible, and highly effective autonomous combat platforms, recognizing that quantity, combined with advanced AI, has a quality all its own. The CCA is not just a new aircraft. It's a foundational element of future air dominance, poised to change the face of aerial warfare forever. Section 4. Hypersonics that fit inside a bomb bay. For decades, speed was king. epitomized by the legendary SR-71 Blackbird. But that was about reconnaissance, about getting in and out fast. Now speed is back, but with a vengeance, and it's all about offense. We're talking about a new class of air-launched Mach 7 weapons that don't just observe, they devastate. These aren't gargantuan missiles that require specialized launchers. They're compact enough to fit on a standard BRU-16 rack, meaning existing aircraft can carry them. This is a game-changer because it democratizes hypersonic strike capability across a wider range of platforms. Take Lockheed Martin's Hypersonic Attack Cruise Missile, HACM. This isn't some distant prototype. It's a concrete example of this new reality. The HAM packs a formidable 1,000-pound blast fragmentation warhead into a sleek 16-foot shell. But its true power lies in its speed and reach. With a range of 1,000 kilometers and a time to target of just 9 minutes, it can hold vast areas at risk, providing an unprecedented rapid strike capability. Imagine the implications for enemy defenses: detecting, tracking, and intercepting a target moving at Mach 7 with minimal warning is an incredibly difficult, if not impossible, task for current missile defense systems. This kind of speed fundamentally alters the deterrence dynamics, enabling rapid strike capabilities that challenge existing strategic balances. And the cost? Here's another shocker. The HACM is projected to cost 1/3 of a Tomahawk Block 4 cruise missile. This isn't just about faster weapons. It's about affordable, faster weapons, making them viable for widespread deployment. This dramatically improves the cost-exchange ratio for high-value strikes, allowing for more frequent and decisive engagements. The first squadron slated to field it? The 356th Fighter Squadron at Eielson Air Force Base as early as 2026. This isn't a long-term goal. It's happening now. And the platforms carrying them are diverse. The stealthy B-21 Raider will carry 4 internally, maximizing its deep strike capability. The F-15EX, a modernized 4th-generation fighter, will carry 2 underwing, transforming its role. And even the smaller Collaborative Combat Aircraft, CCA, will carry 1 underbelly, turning these unmanned wingmen into potent long-range strike assets. Suddenly, every fighter, every bomber, every advanced platform becomes a strategic asset capable of delivering devastating hypersonic strikes. This isn't just an evolution of weaponry. It's a profound shift in doctrine, blurring the lines between tactical and strategic air power and profoundly altering the calculus of global power projection. The age of hypersonic dominance is here, and it's reshaping military strategy as we speak. Section 5. The 6th-generation core while. Much of the next-generation air dominance (NGAD) program remains shrouded in secrecy, particularly its manned component. The fragments of information that have trickled into the open source paint a remarkably consistent and awe-inspiring picture. We're talking about an aircraft that is approximately 40% larger than an F-22 Raptor. Why so big, you ask? Because size here translates directly to capability. More internal fuel for extended range, larger weapons bays for advanced munitions like those hypersonic missiles we just discussed, greater capacity for next-generation sensors, and the computational power needed to manage an entire networked family of systems. Powering this behemoth are adaptive cycle engines, a revolutionary leap in propulsion technology. These aren't your grandfather's jet engines. They can dynamically change their bypass ratio during flight, allowing for optimal performance across a massive flight envelope. From fuel-efficient cruise to blistering supersonic dashes, we're talking about pushing 50,000 pounds of thrust, giving this aircraft unprecedented speed, acceleration, and endurance. This kind of engine technology is critical for achieving and maintaining air superiority in highly contested environments. Stealth, of course, remains paramount, but it's broadband stealth now, specifically designed to shrug off even low-frequency VHF radars that have traditionally posed a challenge to existing stealth aircraft. This means an even higher level of survivability against a wider array of threats. And for something truly futuristic, imagine a laser that can dump 150 kilos out of the nose. This isn't just for show. It's a directed energy weapon capable of everything from dazzling enemy sensors to engaging incoming missiles or even, potentially, targets on the ground. This introduces a whole new layer of defensive and offensive capabilities, changing the very nature of engagement. But perhaps the most profound change isn't in the airframe itself, but in the role of the human inside it. The pilot of the 6th-generation core is no longer just a stick-and-rudder aviator. They are a true mission commander, a highly augmented decision-maker. Their helmet isn't just a display. It feeds a 360-degree mixed reality map, seamlessly blending real-world sensor data with tactical overlays, threat assessments, and mission objectives. It's like having superhuman situational awareness. 80% of tasks are handled via intuitive voice commands, freeing up cognitive load, while eye tracking takes care of the rest, allowing for rapid selection and targeting. The cockpit is transforming into an intuitive, high-bandwidth interface for managing a complex battle network. And yet, despite all this futuristic tech, the jet still carries an M61 heritage cannon. Why, in an age of lasers and hypersonics, would you still have a gun? Because sometimes, the future still needs the brutal, undeniable reliability of 1990s technology. For close-in engagements, for psychological effect, or simply as a last-ditch backup, the M61 serves as a reminder that fundamental combat principles endure, even as the tools evolve. The 6th-generation core isn't just an aircraft. It's a testament to the ongoing evolution of human-machine teaming at the absolute apex of military technology. Section 6. Swarm Escalation. If the idea of a single unmanned wingman is impressive, prepare yourself for swarm escalation. DARPA's Offensive Swarm-Enabled Tactics Offset program wrapped up last year, and its findings were nothing short of eye-opening. The big takeaway? A swarm of 250 small autonomous drones can effectively beat a regiment, and here's the kicker. It costs less than 1 tank of gas per drone. Think about that economic advantage. This isn't just cheap. It's shockingly affordable mass. These aren't sophisticated multi-million-dollar aircraft. Each quadrotor is often 3D printed from durable, lightweight nylon, making them incredibly cheap to produce and, crucially, entirely disposable. And despite their diminutive size, they pack a punch. Each carries a shaped charge about the size of a coffee mug, capable of disabling or destroying light armored vehicles, personnel, or critical infrastructure. This isn't about precision strikes against hardened bunkers. It's about overwhelming an adversary with sheer numbers and distributed lethality. The intelligence of these swarms is equally impressive. They network using resilient mesh 5G technology, ensuring robust communication even in contested electromagnetic environments. They don't rely solely on GPS. They navigate by AI-generated landmarks, making them incredibly difficult to jam or spoof. And here's a critical element of their resilience. They can autonomously replan their mission and retask their objectives, even if 70% of the swarm is shot down. This distributed intelligence means there's no single point of failure, making them incredibly difficult to defeat comprehensively. The tactical implications are profound. Imagine Marines as early as 2025, training to launch these swarms from what look like picnic coolers strapped to the back of JLTVs. This isn't some specialized fixed-site launch platform. It's about tactical flexibility, rapid deployment, and decentralization. The ability to deploy a devastating swarm from virtually anywhere, quickly and discreetly, offers a revolutionary advantage in ground combat. The ethical implications, of course, are immense. The sheer speed of these autonomous systems means that the swarm can decide who lives and dies before a human can even finish their morning coffee. This raises critical questions about human oversight, accountability, and the nature of warfare itself, questions that we'll dive into more deeply later. But one thing is clear: swarm technology is no longer a theoretical concept. It's a rapidly maturing capability that is poised to fundamentally alter the landscape of modern conflict, demonstrating that sometimes small, cheap, and numerous can be far more effective than large, expensive, and few. Section 7. Turkey, UK, and the global race. While America refines its intricate family of systems, it's crucial to understand that this isn't a solo act. Allies and potential adversaries alike are sprinting ahead with their own ambitious, albeit sometimes narrower, goals, rapidly closing the technological gap. This isn't just a US phenomenon, it's a global race, and the implications for international security are immense. Take Turkey, for example. Their Bayraktar Kızılelma, a jet-powered unmanned combat aerial vehicle, UCAV, made headlines last December by flying supersonic. This isn't just a drone. It's a stealth-capable, high-performance combat aircraft designed for both air-to-air and air-to-ground missions. What's more, it's designed to launch from short-deck carriers, significantly extending Turkey's naval air power projection. It fires domestic SOMJ cruise missiles, showcasing a sophisticated indigenous defense industry. And the cost? A remarkably affordable $70 million for 3 copies. This demonstrates a clear intent to field advanced, autonomous air power that can operate in contested environments, challenging regional power balances and providing a powerful tool for force projection. Across the pond, the UK's Project Lanka, lightweight affordable novel combat aircraft, affectionately nicknamed the Spirit Mosquito, has achieved significant breakthroughs. It's managed to shrink its radar cross-section below 0.01 square meters, putting it firmly in the stealth category while keeping its unit price at a mere £10 million. This highlights a different approach, focusing on highly stealthy yet affordable loyal wingmen that can operate alongside manned aircraft like the upcoming Tempest. The UK is demonstrating that high-end stealth doesn't necessarily have to come with an astronomical price tag, making advanced air power more accessible and potentially more numerous. Even South Korea's KAI is getting into the game, revealing a stealthy wingman concept designed to ride shotgun with its KF-21 Boramae fighter. This trend is clear. Nations that have historically focused on developing manned fighters are now rapidly pivoting to integrate unmanned autonomous capabilities into their air forces. The bottom line here is profoundly simple. If you can build a trainer aircraft with all its complexities in aerodynamics, propulsion, and avionics, you can now build a loyal wingman. This isn't just about advanced manufacturing. It's about the democratization of sophisticated military aviation technology. This global proliferation means that the playing field for advanced air power is rapidly expanding. While this strengthens the interoperability and capabilities of allied forces, it also raises critical questions about cybersecurity, supply chain, resilience, and the strategic implications of more nations possessing autonomous combat capabilities. The global race is on, and the landscape of military aviation is becoming more crowded and competitive than ever before. Section 8. Directed energy is finally deployable. For decades, directed energy weapons, lasers specifically, have been the stuff of science fiction, always 5 to 10 years away. Well, guess what? That future is finally here, and it's deployable. Last summer, the U.S. Air Force conducted a groundbreaking test, demonstrating a $300 laser mounted on an AC-130J gunship. In a mere 5 seconds, that laser burned a hole clean through a cruise missile flying at 300 knots. Let that sink in. A laser from an aircraft, destroying a moving target in seconds. The implications are revolutionary. Recoil? Absolutely zero. Unlike traditional kinetic weapons, a laser doesn't generate any physical kickback, meaning no wear and tear on the airframe from repeated firing, and no impact on the aircraft's flight path. And the cost per shot? A staggering $1. Compare that to the hundreds of thousands or even millions of dollars for a single missile. This isn't just an economic advantage, it's a paradigm shift in how we think about air defense and offense. Imagine the ability to engage countless threats without running out of expensive munitions. The primary limiting factor for airborne lasers has always been atmospheric turbulence, which can scatter and weaken the beam. But thanks to incredible advancements in adaptive optics, this challenge has been largely overcome, solving approximately 90% of beam wander. This technological breakthrough is what makes these weapons truly viable. The next step is already in motion, a podded version of a directed energy weapon for the F-15EX by 2027. Picture this: a fighter jet that can stay on station indefinitely, as long as its onboard generator keeps spinning, effectively turning every sortie into a no-fire cost patrol. It can engage incoming missiles, drones, or even ground targets with pinpoint accuracy, without depleting its finite missile load. This transforms the economics of air combat and air defense, offering a persistent, low-cost engagement capability that was once unimaginable. Directed energy weapons aren't just about shooting down threats. They can also be used for dazzling enemy sensors, disrupting communications, or providing non-lethal deterrence. Their speed of light delivery means no lead time, no travel time, just instantaneous effect. This technology, once confined to laboratories and blockbuster movies, is now a tangible, deployable reality, promising to redefine the very nature of airborne engagement and offering a truly revolutionary capability for future air forces. Section 9. Pilot training without pilots. The traditional path to becoming a fighter pilot is long, arduous, and incredibly expensive. We're talking years of training. But the pilot training. Next program is radically reshaping this process. It's graduating fully qualified lieutenants in just 6 months, half the time of the traditional undergraduate pilot training, UPT pipeline. How are they doing it? By leveraging cutting-edge technology and a fundamentally different approach. Students in this program wear haptic gloves, providing tactile feedback as they fly incredibly realistic virtual reality sorties against AI adversaries. These AI opponents aren't just programmed, they're modeled on real dogfight recordings, replicating the tactics and maneuvers of actual human pilots. This means trainees are gaining high-fidelity combat experience from day one, without the immense costs and risks associated with actual flight hours. After each mission, they debrief not with a human instructor poring over notes, but with sophisticated AI that uses eye-tracking heat maps to analyze every glance, every stick input, every decision made during the virtual engagement. The AI instructor, unlike a human, never gets tired, never misses a detail. It grades every millisecond of stick input, every throttle adjustment, every tactical choice. And crucially, it personalizes the very next lesson before the canopy even opens, adapting the curriculum to address individual strengths and weaknesses in real time. This hyper-efficient, data-driven approach allows for accelerated learning and unparalleled personalization, maximizing the effectiveness of every training minute. Graduates of this accelerated program then transition directly to the collaborative Combat Aircraft (CCA) simulator, where their primary task isn't to fly a single jet, but to control 4 drones simultaneously. This highlights the profound shift in the pilot's role. The future aviator isn't just a stick and rudder expert. They are a mission manager, a tactical orchestrator, a human-machine interface specialist. The cockpit, once a sanctuary of individual skill, is rapidly becoming a sophisticated server rack with a seatbelt. It's a node in a vast network, where the pilot's primary function is to supervise, strategize, and make high-level decisions, while the AI handles the minute-by-minute execution. This new training paradigm ensures that future pilots are not just proficient flyers, but expert integrators of advanced technology, ready to operate in the complex networked battle space of tomorrow. Section 10. Ethics, Cyber, and the Kill Chain. Question autonomy scares people, and for very good reason. The idea of machines making life or death decisions without immediate human intervention taps into deep-seated fears. The Pentagon is acutely aware of this, which is why its 2024 policy memo on autonomous weapon systems is so significant. It maintains a strict human-in-the-loop requirement for nuclear platforms, meaning a human must always authorize a nuclear launch. That's a line we're not crossing. However, for conventional strikes, the memo greenlights fully autonomous operations, if the target probability of identification exceeds an astonishing 99.9%. That's a high bar, and it's easier said than done. Why? Because adversaries aren't static targets waiting to be identified. They are actively engaged in sophisticated cyber warfare and deception tactics. They spoof GPS signals, leading autonomous systems astray. They deepfake troop movements and equipment, creating convincing but entirely false realities. They inject false targets and corrupted data into training datasets, subtly poisoning the well of AI learning. These tactics aim to confuse, mislead, and ultimately undermine the trust in autonomous identification systems, forcing human intervention and slowing down decision cycles. So what's the counter-move? The military is exploring several cutting-edge solutions. One is blockchain-based sensor integrity. Imagine a decentralized, immutable ledger that records every data point from every sensor, creating an unalterable chain of custody for information. This makes it incredibly difficult for adversaries to inject false data or spoof signals without being immediately detected. Another solution is the development of ethical black boxes. Much like flight recorders on commercial aircraft, These systems would record every single AI decision, every parameter considered, every action taken, on an immutable ledger. This provides an audit trail, ensuring accountability and allowing for post-mission analysis of autonomous actions, crucial for building trust and refining algorithms. This complex landscape means that the future battle space isn't just about hardware and software. It's about trust, verification, and accountability. And who do you think is going to be at the forefront of navigating this incredibly intricate web of technology, ethics, and international law? Lawyers with security clearances. Expect them to become the hottest job in uniform. They'll be the ones drafting the rules of engagement for autonomous systems, interpreting international law in the context of AI decisions, and ensuring that our technological advancements are deployed responsibly and ethically. The kill chain question isn't just technical. It's deeply philosophical, and the answers we find will shape the very nature of future conflict. Section 11. The Cost Curve Miracle. For decades, the story of military aviation has been one of ever-escalating costs. Fifth-generation fighters ballooned to well over $100 million per airframe, sometimes even $200 million or more, making them exquisite but incredibly scarce assets. This created a strategic dilemma. How do you maintain numerical superiority and deploy forces globally when each platform costs a fortune? But here's the secret sauce, the true cost curve miracle that this new wave of technology is bringing. It reverses that trend. Dramatically, consider the Collaborative Combat Aircraft, CCA, at $15 million a pop. That's not just cheap. It's astonishingly cheap. It's less than the cost of the ejection seat upgrade on a Eurofighter Typhoon. Think about that for a moment. An entire autonomous combat aircraft, capable of carrying missiles and performing complex missions, costs less than a single component designed to save a pilot from a much more expensive jet. This allows for mass production, enabling the military to field hundreds, even thousands of these platforms, fundamentally changing the numerical advantage equation. Then look at the Hypersonic Attack Cruise Missile, HACM. At $14 million per round, it's a bargain compared to the $25 million for a legacy Tomahawk Block 4 cruise missile. Not only is the HACM significantly faster and more difficult to intercept, but it's also cheaper. This means more effective, harder-hitting weapons can be procured at a lower unit cost, making advanced strike capabilities more accessible and sustainable. And let's not forget the swarm drones, clocking in at a mere $15,000 each. They are cheaper than the Hellfire missile they can effectively replace in many scenarios. This isn't just about cost savings. It's about enabling entirely new tactics. You can deploy hundreds of these disposable drones for the price of a single Hellfire, overwhelming defenses and achieving objectives through sheer numbers and distributed intelligence. This ability to perform high-risk missions without endangering pilots, and at a fraction of the cost, is a game-changer. This isn't just about saving money. It's about a fundamental strategic reorientation. The force can now genuinely trade expensive brains, those exquisitely complex multi-million-dollar manned fighters, for cheap mass. This upends the tyranny of ever-rising unit cost that has plagued military procurement for generations. It means we can field more capabilities with greater resilience and at a more sustainable price point. This cost curve miracle is perhaps the most understated, yet revolutionary aspect of the new era of military aviation, promising to redefine force structures and operational strategies for decades to come. Section 12. A Day in 2028. Let's fast forward to a typical Pacific morning in 2028. The sun is just beginning to paint the sky over Kadena Air Base in Okinawa. An NGAD flagship, sleek and silent, departs the runway, its powerful adaptive cycle engines humming almost imperceptibly. Tucked neatly under its wings, almost like digital fleas, are 4 collaborative combat aircraft, CCAs, its loyal, unmanned companions. The manned pilot inside the flagship is not primarily flying the jet. They're the mission commander, their mixed reality helmet feeding a constant stream of fused sensor data, providing unparalleled situational awareness of the vast expanse of ocean below. 500 nautical miles to the west, an enemy destroyer, part of a formidable naval task group, suddenly lights up its fire control radar, sweeping the skies for threats. The AI backbone, seamlessly integrated across the NGAD family, instantly detects the emissions, processes the threat, and analyzes potential engagement options in milliseconds. Without a human touching a single control, the AI assigns roles. 2 CCAs are tasked to immediately begin jamming the destroyer's radar, overwhelming its sensors with electronic noise. Another CCA is designated to sacrifice itself, sprinting ahead to present a larger radar reflector, acting as a decoy to draw fire. The last CCA, meanwhile, accelerates to Mach 7, launching a hypersonic attack cruise missile, CHAC-M, directly at the destroyer. The total engagement time from radar detection to missile impact? A staggering 38 seconds. The destroyer never even gets a chance to fire. Its radar is jammed, its attention diverted by a decoy, and before it can react, the hypersonic weapon arrives. The pilot in the NGAD flagship never touched the trigger. Their role was one of oversight, validation, and strategic command, allowing the AI and the autonomous systems to execute the tactical details with unparalleled speed and precision. Back at base, the maintainers are already at work. The CCAs, having completed their mission, return to base. Their battery packs are swapped out in minutes, faster than loading suitcases into a taxi ready for their next sortie. This isn't some abstract wargame simulation or a speculative concept. This is next year's syllabus. This is the operational reality that air forces worldwide are rapidly preparing for. A future where human ingenuity and machine autonomy merge to create an air power capability that is faster, more lethal, and more resilient than anything we've ever seen before. The skies of 2030 won't just be owned. They'll be dominated by those who master this seamless integration. Call to action. After all that, what piece of this incredible future surprises you most? Is it the sheer bargain of hypersonic missiles, or the idea of swarms cheaper than a used car? Maybe it's the thought of lawyers becoming the new combat aces. Drop your take in the comments below. And if you want to ride shotgun through tomorrow's tech, hit that subscribe button and ring the bell so you don't miss when we tour the B-21 factory floor. Conclusion. The takeaway, let's be clear, the fighter pilot is not disappearing. Far from it. Instead, the cockpit itself is expanding, evolving from a solitary bubble into a vast networked ecosystem. This isn't about replacing humans with machines. It's about augmenting human capability, amplifying decision-making, and extending our reach in ways that were once unimaginable. Autonomous wingmen, lightning-fast hypersonic weapons, and the seamless fusion of AI across every platform are not just sketches on a whiteboard or abstract concepts. They are tangible realities, taxiing on runways today, undergoing testing, and being integrated into our defense strategies right now. The nations that master this complex integration, this delicate dance between human intellect and machine efficiency, between cutting-edge technology and astute operational doctrine, will undoubtedly own the skies of 2030 and beyond. They will possess an unmatched advantage in global deterrence and force projection. The ones that don't? Well, they'll unfortunately be left studying history, quite literally from the ground. The future of military aviation isn't coming. It's here, and it's spectacular.